cells have flow meters and 2 detectors. So one of the things you have to, any absorption measurement is that, some gases absorb light differently, even particles. So sometimes it depends on the measurement how the manufacturer did that. You have to worry about interferences. And ozone absorbs light at 154 nanometers. And there's other things that absorb from that wavelength, like aromatic hydrocarbons and some other things. So that's the basic principle of everyone.
So the scrubber selectively will choose between
Correct.
the ozone. What is the scrubber medium?
It's a. We had one go out on us the other day, when we could see the pieces falling out. It's basically kind of like a steel wool. It's a lot of surface area, is what it is. In fact, that's like activated charcoal.
Yes,
that's
like
one
charcoal.
reason activated charcoal works is if you get it under a microscope, it's all surface area. And so we do use charcoal sometimes to scrub ozone when we're making zero air, but that also scrubs out SO2 and some of the hydrocarbons and things like that, that in this case we want to leave those in. So the air comes in and it comes in through these valves. It gets split between 2 flow paths. One flow.
This is the ozone.
This is ozone.
That's the CO.
That's CO. So the ozone, so it comes in, one path goes straight into the cell. The other path gets routed through this scrubber. So it selectively removes the ozone. So one cell is measuring the absorption from ozone plus all the other absorbers. The other cell is measuring the absorption from all the other absorbers. So the difference then is ozone. And there's one light source and it's split by 2 mirrors right here. So that takes out some of the variability. But there are 2 detectors. And one cell could be dirtier than the other. We put filters on it, but still they're going to get a little bit dirty. And to take out the differences in that, these 2 solenoids flip-flop. They fire at the same time, and they flip-flop which cell is reference and which cell is not. And so then it takes the average of that, makes 4 measurements, both cells twice. Average of that is in the signal that it puts out. This is an older one. You'll see the difference when we get into this one. This is the main power supply. This is the lamp driver power supply. It's very old technology, big, heavy transformers. Individual data cards up here, like an old computer where they pop into the motherboard. Pretty basic. You can either do analog, where you get like a 0 to 5 volt output that's proportional to the measurement on the screen, or you can talk to it serially, where you get ASCII text out, and that's what we usually do, because that way we can get the rest of the parameters, like Sergio pointed out, the flow sensors, the pressure sensors, things like that. We can read out the internal temperatures. And from that, we can leave this in one of our remote sites. We can log onto the computer, and we can see pretty much everything about how the thing is working without actually having to be there. There's most things we can do remotely, but there's a few things we still have to do.
Does the light shine a full spectrum through them?
No, this is actually a mercury lamp.
Oh, okay.
It's a little gel light mercury lamp. When we have this instrument doesn't have it, but we can get this instrument with an internal ozone generator, so it can do self-calibrations. Self-check. It's not really a full calibration. It's not a good, stable, repeatable source, but it's close enough to know if it's working. That uses the same lamp. The only difference is the one that's up here that generates the ozone does not have the coating on it, so the mercury emits at 254, but also at, I think, 185 nanometer, and the 185 nanometer is more like what you get up higher in the atmosphere that creates the ozone layer. And so that one that's how they make the ozone. The lamp over here for the detectors has a coating on it that filters out the 185, so you're only getting the 254 line. And that's so we can make the absorption measurement, but not worry about making ozone in the cell.
Oh, it's all Beer Lambert.
It's all Beer Lambert. And in fact, this one is also, so this is the CO instrument. It's also Beer Lambert. This one is, so this is a UV absorption instrument. This one is an IR absorption instrument. see, this one's a little more modern on the inside. These big power supplies here are now here. This is now a modular power supply. This power supply is specific to this instrument. That's the same power supply they put into all the new I-Series. I-Series had the big changes for the I-Series were the power supply, kind of the standardized boards, and network communications. These have Ethernet connections on them. You can put them on and drive them through the network if you want to. This is the program card for the IC. This board and this board are specific. All the other electronics in here are common to all the different instruments. This one, the sample comes in, and this is a permeation dryer because water absorbs IR. So what we do is it comes through the center tube. The outer tube is at lower pressure, and it's already been through the instrument, so it's already been dried. So then it pulls the moisture from the ambient sample out to the outer sheath and then gets ejected out in the exhaust. So it comes through, it gets dried, it goes around and around. Then it comes in through into this bench. It comes in from underneath. This bench has an IR source right here. That's what these two connectors are for. Basically, it's a little heating element. They go out periodically, and it looks like a little resistor, but it's just wires wrapped around like a ceramic core, I think. This motor spins a gas correlation wheel. What the gas correlation wheel is, it's a metal disc. It's got two glass cells in it. One cell has nitrogen, the other cell has nitrogen and a known amount of carbon monoxide in it. Overlaid on that is a chopper. So there's these blades that go through it so it can get pulse measurements, so the light comes in and measures it. It's fast enough that you get several measurements from each cell for each revolution. And it spins 1,800 RPM, so it's fairly fast. The light comes in. This is an angled mirror here. It actually makes 4 passes off of the end reflectors before it reaches another mirror under here that's angled upwards. This is the detector. And so what it's doing is it's measuring, while you're measuring with the IR source shining through the nitrogen cell, you're measuring ambient CO. That's the absorption. In theory, we've taken all the other absorbers at this wavelength out through the dryer. So we're measuring CO. And the other half of the wheel, we're measuring ambient CO plus the CO in the wheel. So it's taking the ratio of those in order to get what the ambient concentration is. The other thing that this instrument will do, this is a trace level enhanced. There's a block here along the side. This is heated. If you notice, this has cooling fans and everything in it. This fan actually takes air out rather than blowing it in. The lid is insulated. It's a thermal measurement. It needs to be at a fairly constant temperature. When we're running it, if it's been up and running and everything's happy, it runs at 50 C. That way it's always heating. If we pop the lid off of it, the measurements start kind of walking all over the place because now we're changing the temperature plus the IR. What this does, there's a valve up here that lets us select routing this through. So the bench is hot. This is connected to it, so this is also hot. This is a catalyst like in your catalytic converter in your car. It oxidizes CO to CO2. We don't measure CO2. So this is our zero. So what we'll do is either through the data acquisition program where we can send the commands, or we can use the internal program in here. We can have this instrument once an hour, hour as fast as we can go if we let the instrument do it. We can do whatever frequency we want if we do it through the computer. We'll go in, we'll route the sample through the reactor for the catalyst, and we can get our zero, check our baseline. It does drift. I had one of these and I was playing with it one time early on just to see how bad it would go, and I let it run for about a week without resetting the zero. And it was reading 7 parts per million in the lab with a 0 of 6.8 parts per million. And it would just keep walking off just forever. So we reset, generally we reset about every hour. So we reset that baseline. And by doing that, we haven't let it walk very far. And so it's only a few, 5, 10, maybe 20 ppb difference. And at the levels that CO is, that gets to be 20 is really a really, really bad one. Typically it's 5 or less. And we're okay enough with that to say that that data is good enough so we can send that data as it is off to TCEQ without having to go back and doing any post-processing on it and resubmitting it. So these are basically the 2 gas measurements that we have at most of our monitoring sites around the city.
So they take a discrete sample every hour.
They're actually continuous
They're
measurements.
continuous?
And so we run these both are run at 10-second updates, so it's a constant
Okay.
flow. We get 10-second averages. We hold the instruments every 10 seconds. That data gets, and I think Laura's going to show some of this when you get to that. It talks about the websites. That data comes into central campus from all the points afar, gets averaged into, we flag out the data that's non-ambient when we're doing quality control checks and things like that. Average that to 5 minutes, package it the way TCQ wants it with their flags, and we spit it off to their server and it goes into their systems. And so CAMs 695 through 699 are our sites. We're now taking over and reactivating CAMs 670 through 672. The launch trailer, which we were going to go to, but it just worked out better to stay in one spot today, will probably become another CAM site in the near future as well. So that's a lot. In general, they're all fairly similar. You have an inlet, you have your measurement bench and your detector. You have your sensors to help you do your diagnostics, whether it's pressure, flows, and temperatures. You have a pump to move it through. The pump, and just about everything we do, we put the pump at the very end. That way we haven't affected the sample as it comes in. Some instruments, CO is not so reactive, so we could push through, and in fact, when we modify, was it this one? Yeah, it was this one. We put this one on the NASA DCA this last summer, and we modified it with pressure and flow controls and everything in order to make that work so we could take it to altitude. We had to put a pump on the front end of it and push the air in so that we could pull enough air from outside and push it in so that the instrument never really thought it was much above Denver, even though we were at 30,000 feet. So that's the fun part of our job. We hardly ever leave instruments alone. We always get in and do something strange to them inside.
So why you glad your clients?
Ground measurements are easier to take.
Yeah, I was actually going to ask, when you send the numbers to TCQ, do they put them in a model or something to estimate what's really at ground level, or do they?
So, yeah, our sites, we're not regulatory. We don't want to be regulatory. When we did the early aircraft work for about 10 years or more, we were part of monitoring operations, and we had to go through, and we had technical system audits and all kinds of stuff that we had to go through, and that is not so pleasant. It's not hard, it's just there's a lot of hoops you have to jump through. We operate differently. We actually, those guys, when they're regulatory, their operating procedures are set in law. Ours, we're free to do better than that. The laws don't get changed that often. When we find a better technique, we can automatically adjust and take that better technique. Because of that, we're not going to be defensible in court, so we're not considered part of we're an informational site. They use us our sites will, if our calibration flag doesn't propagate through correctly, sometimes our calibrations, it has happened, usually when we're doing maintenance on the site or something like that, and it doesn't get caught. we'll do a span of 160 ppb on ozone, and if that hits the system, it kicks off like a level orange or red alert from the TCQ automated system. It's a little embarrassing. It has happened before, but we try really hard not to let that happen. So our sites are used for advisory purposes like that, and they do use this for modeling. One interesting thing about this particular location is most air quality models, we're measuring from 67 meters above ground, I believe. That puts us in the second layer of most models, and it's not a place where they normally get data. So that's been interesting. We've seen some differences between the measurements here at Moody Tower and the one down at the launch trailer, which is a surface site about a half mile north, still on campus. It's measuring from 15 feet off the ground. This is 230. And we did some work that was part of my dissertation, was trying to explain why this is, and a large part of it, especially at night, is I don't know how much y'all know about ozone chemistry, just the basics. Ozone will react with NO2, or with ozone with NO gives you O2 and NO2, and NO2 then in the sunlight gets photolyzed back and makes ozone. So there's a quantity that people like to talk about called ox, which is the sum of ozone and NO2, because you've got ozone and then basically you've got potential ozone, because that NO2 when it photolyzes will go right back to ozone. So when we look at ox is generally pretty well conserved, so it's just a partitioning. The ground site has less ozone, more NO2, the higher site has more ozone, less NO2.
That's really interesting.
All right,
So-
we're going to switch up the groups.